Bob's the boss. He'll probably run you back to Scott, but what you do then is you say, "Hey, Scott, Rob said I needed to talk to you about getting more of these books printed up." And it carries a little bit more weight. That's how Paul teaches you to be sneaky. And you don't have any.
You're looking for a place to go for the total eclipse on April the 8th, 2024, Explore Scientific has a site for you. We have an expedition going to Texas Hill Country to experience the dark skies. We were at the same location for the annular eclipse where Kathy Machen and her husband Gil attended. Here's what they had to say about the site.
I'm down here with my husband in the hill country of Texas. Beautiful area. And we managed to actually see the annular eclipse from start to finish. It's always neat to see the sun moving in. It's, you know it's coming, it's relentless, you can't stop it. And let me get a picture, and you look at the sun through the eclipse glasses, and there's that ring of fire. And if you're lucky enough to look through, say, a hydrogen alpha, you see that ring of fire with prominences all the way around. And it's like, okay, this is what we came for. And we're happy we did. If you can possibly make it to the 100% total, do it.
It's going to be great to see Kathy again on April the 8th, 2024 for the total eclipse. If you want to come join us, go to explorescientific.com and search for eclipse. We're going to have a great time. Hope to see you there. On April 8th, 2024, you have the chance to see an astounding sight, a total eclipse of the sun. Explore Scientific has a spot in Texas Hill Country that's going to be a great location. We were there for the annular eclipse, and we had a great time. Paul Perrick, who traveled more than 1,000 miles from Hilton Head, South Carolina, had a great time, and he's coming back to the same spot for the total eclipse.
I pulled in here at like 10:30, 11:30 at night, and the Milky Way was screaming out of the sky. The clouds were gone. This morning it was a little cloudy, but it cleared up. I've got a boatload of photos I've got to process now and turn into something usable and beautiful. I am so glad I came here. It was fantastic. Looking forward to the total eclipse in April.
Awesome. Paul, we look forward to seeing you and everyone else at the total eclipse on April 8th, 2024. It's a great location. If you want to come, go to explorescientific.com, search for eclipse, and get your tickets today. A total eclipse of the sun is going to sweep across the United States on April the 8th. You can join the Explore Scientific team in South Texas for the crossroads of the eclipse's star parties. We were at the site recently for the annular eclipse, where Bill Russlink got an astounding taste of what's to come.
This is actually my first star event, and second eclipse. This is an absolutely phenomenal place. I've not ever seen anything as dark as this area. Right now I'm trying to make heads or tails out of the photos that I took this morning. And, some of them a little work in Lightroom, how to be usable. Yeah, it was really really amazing thing. I had never seen an annular before, and it was definitely a one-of-a-kind experience, you know. But this was just phenomenal. In fact, you could say that ring of fire as you described it was just beautiful, you know.
Thanks, Bill. It was a great time, and on April the 8th, it's going to be a great time. Go to explorescientific.com to get your tickets to the crossroads of the eclipse of star party for the total eclipse of the sun.
Welcome, everybody, to the 91st episode of the How Do You Know program. I'm Dr. Daniel Barth, and we want to remind you that the Great American Eclipse is coming up on April 8th. This is very exciting. We're all excited about it here on the program at Explore Scientific, our sponsors. If you would like to go to the Texas Crossroads of the Eclipse party with all sorts of exciting people, you need to look at the explorescientific.com website, and there's a tab up at the top that says Eclipse. And if you want to get in to this wonderful eclipse party in Southwest Texas, it's out in the boondocks, great observing. Encourage you to log on and check that out today. As always, our program is sponsored by Star Mentor. I'm pleased to say that the book recently rose up to number 26 in astronomy and astrophysics on Amazon, and it's available there for you. We encourage you to pick up a copy. Let's go ahead and take a look at today's news. It turns out that Star Trek is real again. In Star Trek Voyager and other science fiction programs, the idea of having a neural computer that functioned like a human brain has been a common theme in many science fiction genres. And now, for the first time, DNA programs or DNA computers are being made to work. We starting over?
No.
Just DNA computers. My producer and I are.
You forgot we had the opening.
I did. We're going to go ahead and get started today with our news of the day. As always, we hope you'll pick up a copy of Star Mentor. And let's take a look at DNA computers today. DNA computers are something that's been in science fiction for years, and they are finally becoming a reality. Researchers have designed a computer processor that actually works and solves problems and stores data on strings of DNA. Now, this is not human DNA. This is just generic DNA strings of nucleic acids. The information storage density is tremendous, at least 10 times or an order of magnitude better than anything in the even the cutting edge methods. And you might say, oh wow, are we now going to have computers that we have to feed and water and change and all that? Well, not exactly. These aren't going to be in your store soon because the processing speed is really, really slow. It can take a DNA chip literally hours to compute the answer to a mathematical problem and then store the information as strings of base pairs on a DNA molecule. So a fascinating leap forward in technology, but probably not in your next laptop. Next up on the news, we're going to talk about asteroid Bennu. We've talked on this program many times about the OSIRIS-REx mission out to asteroid Bennu and the 7-year journey to get there and get us data back. And then NASA was having trouble getting the product, the sample out because there was a couple of stuck bolts. They finally figured that out. And it turns out that the preliminary analysis is showing it isn't just a pile of rocks. Bennu has clays and other minerals that can only form in a water environment. So we're looking at now evidence that a lot of the material from Bennu may have been part of an ocean-bearing world at one time. The average sample size being given out to labs around the world is about 70 milligrams, or 71,000ths of a gram. This is a tiny little bit of dust and powder, and scientists are going after these with electron microscopes and microanalysis. What's happening? Are we really sending out that many samples? No, actually we're not. We're actually archiving and storing more than 90% of the sample retrieved from asteroid Bennu. And why are we doing that? Well, we assume that science is going to progress, that instrumentation and analysis techniques are going to continue to improve. And if you're not getting quite the point, think about this. There are samples gathered from the moon in 1969 that are still being taken out of pristine storage and given to scientists today in 2024 because they've come up with new instrumentation and techniques of analysis. So that's really exciting. Asteroid Bennu will be delighting the science community for decades to come, probably far beyond my lifetime and maybe yours too. The idea that we're actually planning for advancements is just a spectacular idea and concept. Have you ever taken an astronomy course where you learn about the names of the planets, Mercury, Venus, Earth, Mars, Jupiter, Saturn, etc.? And maybe you've learned about different planets have different numbers of moons. Earth has 1, Mars has 2, Jupiter and Saturn is the current king, something like 170 recognized moons. Not all are named yet. But Venus and Mercury have never had a moon. Well, it turns out Venus actually has a new moonlet, or as scientists are now calling it, a quasi-satellite. We did an entire program a while back on moons and moonlets and asteroids. Quasi-satellite is really interesting. It's something that has the same orbital period as a planet. Now, all orbits are elliptical, but the orbits of the major planets are circular to a pretty good approximation. So you have one planet like Venus going here in a nice circular orbit with a definite period. A quasi-satellite has a much more elliptical orbit, but it has the same orbital period. It takes the same amount of time to orbit around the sun, and so in fact, its motion is entirely dictated by the gravitational field of the parent body, in this case, Venus. The quasi-satellite was actually discovered in 2002, and it was given this lovely name of 2002 VE. Well, this is a funny story because an artist who made a poster actually of the solar system actually put in there, he saw this dating and went, ooh, that's interesting, Venus has a moon. And he looked at 2002 VE and he miswrote it as ZOOZVE. And so Venus's quasi-satellite has been officially christened ZOOZV. And there's several different ways people are pronouncing this, and the astronomers who discovered it and helped name it are kind of going, you can pronounce it however you want. ZOOZV is an orbital resonance satellite. That means because it shares the same period, the same orbital period around the sun as Venus, Venus tugs on it in a regular pattern, in a regular time, and keeps it locked in this orbit. If you want to think about orbital resonance, think about taking a child to the park and pushing them on a swing. We don't just randomly shove out our arms and push at any old time. That would probably result in black eyes and kids knocked off the swing, and no one would be happy. But we wait and we time our swing. The child comes back and we push. And we are pushing at the exact right time to give the child a boost to enjoy their swing ride. Well, Venus gives ZOOZV a gravitational push at the exact right time every orbit, and as such, it is locked in and maintains It's one-to-one resonance. In other words, it goes around the sun in the same amount of time as Venus does. Now, the interesting thing between a quasi-satellite and a standard satellite like our moon orbits principally around the Earth. Xusvi and other quasi-satellites orbit principally around the sun, but their orbital motion is controlled by the planet. And so in this case, Xusvi, or 2002 VE if you like, Xusvi is actually orbiting around the sun, but it's always quite a ways from Venus. It's not like the moon, which is quite close to our Earth all the time. Xusvi travels enormous distances from Venus because of its different orbital shape, being much more elliptical. That means that quasi-satellites, because they are spending a lot of time far away from their parent body, well, they're more liable to be disrupted. If Xusvi is visited by a passing comet, if one of its orbits, it drifts closer to Mercury or to the Earth, the gravitation of a different planet can pull Xusvi out of its orbit. It may be flung into the sun. It may be flung out into the outer solar system to be part of the asteroid belt. These things are not permanent in the cosmological sense. We believe that an average quasi-satellite, and again, this is not based on observation, but mathematical analysis. We think they're stable over a period of some tens of millions of years. But if you compare that to the moon's stable relationship with Earth, which has been going on for over 4 billion years, a 10 million year lifespan as a quasi-satellite of Venus is a relatively short amount of time. So these quasi-satellites, it turns out, yes, Earth has one. And we're going to look at some of that in a future episode because it's really exciting. One of the other really fun things about the news this week, and there were so many things going on, but we actually have managed for the first time to observe a star just before it went supernova. You may remember a couple of years ago when the star Betelgeuse, which is the bright red star in the left shoulder of Orion, where it dimmed suddenly. It dimmed by about 60%. And people were very excited. Ooh, is Betelgeuse going to go supernova? It's far enough away to be safe and close enough to be really spectacular. So we were all hoping, but it turned out didn't happen for Betelgeuse. Well, in fact, scientists observing a galaxy about 57 light years distant revealed a progenitor star which subsequently experienced a type, and I think that has to be 57 million light years. That's not 57 light years. That's way too close. 57 million light years away. Typo. It experienced a type 1Bn supernova. This is quite rare and spectacular, and we don't see very many 1Bn supernovae. And so the idea that, we saw this go boom, and then we look back and we realize, we've been observing that exact star for about half a year already. And we had taken a look at it, we had taken a look at its spectra, and we could look back at observations from different telescopes around the world and see how this star was changing literally in its final days. So this idea of observing a progenitor before it explodes is really tremendously important for astrophysics. Think about it this way. We have all of our mathematical models, and mathematical models are lovely. They're fun, they're interesting, they make predictions, but nature doesn't always care what your model does. Nature goes ahead and does its own thing. When we can observe a progenitor before it goes bang, then we can go back to our theories and we can look at actual observational data and look what the theory predicts should have been happening. And this is marvelous because it helps us weed out theories which do not conform to what we're actually observing in nature. So this is really cool. It's like saying, oh yeah, I want to see that ticking time bomb before it explodes. So that was also a very exciting bit of news. Something that's not in the script, but producer Paul, you may have heard of this. The Ingenuity helicopter on Mars has come to its final resting place. And anybody who's flown an RC plane, you know exactly what happened. Hard landing, bang, you get the hard crash landing, and the rotors tip over and they get scraped up. And if it's a RC helicopter, you go darn, and you spend some money for your helicopter or your drone, and you put a new set of blades on it. But when your helicopter is 50 million miles away, that's not an option. So Ingenuity has landed, and they named the landing spot the Hills of Valinor, which are the hills of undying glory from Tolkien's Silmarillion. And so their Ingenuity shall rest. All right, let's go ahead and transition to our topic for today.
That was in the news.
That was in the news. That was in the news.
We'll figure this out eventually.
We will. We're getting better. We're getting better. We've only been doing this for 3.5 years, so we'll get it.
Hey.
There we go. So let's talk about today's hot topic, the main topic for our show, and that is unifying relativity and quantum mechanics. We think about this and people go, meh, why is this important? Well, the idea in physics of unification has been one that's been going on for more than a century. There were originally 4 fundamental forces in the universe, the strong, the weak, electricity, magnetism, and electricity and magnetism were unified by Faraday, and then the electro-weak, the weak force was unified. And so gradually, the 4 forces, apart from gravity, have all been pretty much unified. Why? Because in the very early universe, it was very simple. As the universe cooled down, these separate forces split off and became independent. But gravity has always been resistant to unification. Gravity's like, nope, homie, don't play that. I'm not going to work with that. I'm not going to do your math for you. And the current drive, or the drive current, the drive for the last 100 years has been to unify the theory of relativity by Albert Einstein with the quantum mechanics theory pioneered by Niels Bohr, Heisenberg et al. Why are these 2 theories important to unify? They are both the most accurate, far-reaching, and powerfully predictive theories that we have ever developed. Einstein's theory of relativity is famous for, first of all, nobody liked it, and second of all, it has survived every test and attempt to disprove it for going on for 120 years now. But general relativity is about really, really big things. It's about gravitation. It's about how mass warps space-time, and it's the curvature of space-time which creates gravitation as we experience it. So the best way to explain it comes from John Wheeler, who is a student of Einstein, and he said that mass tells space-time how to curve, and the curvature of space-time tells mass how to move. So gravity is about really big things: stars, planets, galaxies, the origin of the Big Bang. Quantum mechanics is about the really incredibly small. Quantum mechanics works on 10 to 15 orders of magnitude smaller than everyday reality. If you have your meter is 1, take 0.0000, add 15 zeros, and then a 1. When you get down to that ultra tiny realm, that's where quantum mechanics lives. Quantum mechanics deals with things like wave-particle duality. It deals with things like the Heisenberg uncertainty principle, with the idea that We cannot predict that there's randomness fundamentally at the core of the universe, which Einstein hated that idea. God does not play dice, is his famous quote. He didn't like the idea of randomness as part of the fundamental fabric of nature. Well, if one is the theory of the really, really big and the other is the theory of the really, really small, why are we bothering? Because they all come together in black holes. Black holes are the intersection point between these two theories. So, what does a black hole have to do with it anyway? Well, we look at this and we see that black holes combine both the idea of the incredibly massive and tremendously large with the ultra small realm of quantum mechanics. How so? Black holes are massive objects. The smallest ones we've detected are the size of stars. And just to give you a kind of a frame of reference, if we look at our solar system, if you take a look at the sun and Jupiter, that's 99.99 some percentage of the mass of the entire solar system. All the comets, all the asteroids, all the dust, gas, minor planets, moons, Jupiter and the sun outweigh them. And really, the sun is a very massive object with a bunch of little tiny junk orbiting around it. That's the smallest black hole we find. Black holes that are found in the center of galaxies, the supermassive black holes, or SMBHs, these things can be millions, even billions of solar masses. They are the most tremendously large things. And the gravitational field of a black hole, these black holes provide the gravitational field that allows galaxies to organize. Without black holes, current theory suggests you can't have a galaxy, which is really quite fascinating. So we've got these very massive objects that are actually bending space-time. And the bending of space-time has been really accurately predicted by Einstein's theory of relativity for a century. And there are very few cracks in that armor. And when black holes combine, they create gravitational waves. We did a program a few weeks ago on LIGO and Virgo, the gravitational wave observatories, and how those telescopes, if you will, which are L-shaped tunnels with laser beams in them that are kilometers long, 2.5 kilometers long for LIGO, these enormous telescopes can only just capture the signals of colliding black holes. You think about the amount of energy if two star-like objects combine. But black holes are also infinitely tiny. All the mass inside them is crushed down into an infinitesimal point. And so infinity, the density goes to infinity, the size goes to a negative infinity. And so when you try to put together quantum mechanics and gravitation, the math just ends up to be a bunch of divide by zero problems. Try it on your calculator. It doesn't work on your computer. It doesn't give you a reasonable answer. Divide by zero is generally a giant red flag being waved in your face that your theory is wrong and you've done something incorrectly. And so when you try to put quantum theory inside of relativity, the mathematics crash and give you a bunch of infinities. Likewise, if you try to take relativity, interpret it through the lens of quantum mechanics, the theory crashes and you don't get any good answers. So we've had this problem for more than a century. What in the world are we doing about it? It turns out that for most of a century, the problem lies with the older theory, Einstein's general relativity. This has been the assumption, and producer Paul and I were talking about What's the name of the bias?
Oh, cognitive.
Cognitive bias, where you tend to see the things you want to see. Einstein's theory was never popular with mainstream physicists, or at least not for a very long time. And people come up and try to cut their teeth by finding a crack somewhere where relativity theory doesn't quite work. And it's been kind of like one of these Invincible Knight stories where Einstein takes on all comers and they all end up in the dust and in a heap after challenging relativity theory, and it's never worked. But the assumption is if relativity and quantum have a conflict, well, Einstein's relativity theory is what's known as a classical theory. It doesn't break down into a smallest possible piece. No one's ever found, unlike matter, where, we have atoms, we have protons, we have neutrons, we have quarks and neutrinos, but it's somewhere there is a smallest possible piece. We've tried to do this with gravitation. Is there a smallest possible or quanta of gravity? And no, we've never found it. And so relativity seems to be smooth. If you think about it another way, relativity is analog. It's like the speedometer on an old car where it smoothly moves up and down, whereas on a modern car with a digital dash and a digital speedometer, you're going 50.2 kilometers per hour, 50.3. Can I go 50.2758? No. Why? Because it's digital and that system has a smallest possible increment. For your speedometer, well, matter and everything we can physically look at has seemed to have this quantum nature to it, a smallest possible piece of anything, except gravitation doesn't fit. It's like this old analog system where you can have any value you want, and it is stubbornly refused to break down into quantum nature. And since quantum has been successful, quantum theory has been successful literally everywhere else. Chemistry, physics, everything seems to have a smallest possible, except gravitation. And so the assumption has been, literally for decades and decades, that somehow we need to find a way to quantize gravity. None of these efforts have been successful at all. No one has been able to quantize gravity in any way, shape, or form. All the efforts collapse, the mathematics fail, they end up giving you lots of infinities, and it just simply does not work. So, yes, of course, if it's on my program, how do you know? We've got to have somebody with a new idea. And this person is Professor Jonathan Oppenheim. Not Oppenheimer for those of you fans of the movie from last summer, but Jonathan Oppenheim. He's part of the faculty of University College London. And he has a new idea. Instead of needing to quantize gravity, he says, no, Einstein wins again. Einstein was right all along. Space-time is classical, and it does not need to be quantized at all. Professor Oppenheim says, in fact, space-time actually really is continuous, analog, smooth, just like Einstein thought, and just like the relativity theory has insisted since basically 1905. He looks at this and says, nope, there's no need to break down space-time into pieces of smallest possible length. Now, the minimum size that we've been able to come up with for physical space is called the Planck length, or Planck length, if you're going to give it the proper German pronunciation. The Planck length is 1.6 times 10 to the negative 34th meters. If you really start to just write this number down, 0.0000, 34 zeros, and then a 1. The shock absorbers on your brain just kind of bottom out and crash when you try to think of things this small. This is 20 orders of magnitude smaller than a proton. No one, to my knowledge, has ever imaged a proton. But you're talking about, you get to the proton level, you've still got another 20 zeros before you hit that 1. The Planck length is incredibly tiny. And there is apparently, some people theorize, a Planck time. Except when you try to put the Planck length and the Planck time, which makes the Planck space-time quantum unit, and you put it into relativity, it doesn't work. Professor Oppenheim says there's a really good reason it doesn't work, and that's because space-time doesn't have a minimum possible size. He instead says, well, if modifying Einstein's relativity hasn't worked, let's go ahead and modify quantum theory. He gets a lot of resistance in the science and astrophysics and physics community for his line of thinking. He refers to this by saying that the Planck scale is actually mediated by space-time itself. And to unpack that statement mathematically, it would take both more time than we have here and more mathematical chops than your pal and narrator actually has. This idea of his, he refers to as a post-quantum theory of classical gravity. And I just love that. Postmodernism has been a philosophical movement and a mathematical movement. And postmodern physical theory, the Standard Model, etc. And he says, yeah, now we need to go post-quantum. After a century and then some of going, yes, quantum is the answer, Professor Oppenheim says, nope, Einstein wins again, and at the very most fundamental level, quantum breaks down, relativity does not. So that's a really fascinating idea. But when it comes to these interesting ideas, of course, when we look at this, we have to think about, can we test these ideas? Let me back up just a little bit. The idea of theory, hypothesis, fact. Everybody who's a fan of this program has heard me talk about this before. Someone who says, that's not a fact, it's just a theory. That's kind of the loudest, boldest proclamation of scientific ignorance it's almost possible to make, because a fact is a small thing. Here's a pen. It's made of styrene plastic. This is a fact. We can analyze it. Everyone can take a piece of this pen and analyze it for themselves. You're all going to come up with the same answer. It's a fact. It doesn't predict anything. It doesn't predict what the next generation of pen is going to be made of. It doesn't predict how pens will be used or anything else. It just says this is made of styrene plastic. Hypotheses are an idea about how nature works. It's bigger on an order of magnitude than a fact, and hypothesis must take account of facts, because if you have a hypothesis and you ignore facts, what does Sherlock Holmes say? To theorize in advance of your data is a capital mistake. Well, if you go ahead and you have an hypothesis, it better take account. If you have a hypothesis about how all pens are made and manufactured, you better have a lot of facts about different kinds of pens. And when you have those facts, your hypothesis better not ignore any of them. It's not going to be very functional. So a hypothesis says, here's how I think things work. A theory is a much grander thing than an hypothesis or simply a fact. If you think about, a fact is a brick and hypothesis is a building, well, a theory is a giant city spreading out over the land. And a good theory takes account of not only all the facts we know about a certain topic or idea, it also folds into itself all the hypotheses about these facts. And a good theory is kind of a sieve for these hypotheses. And the theory goes ahead and says, I can predict. And the theory allows you to test hypotheses and say, yes, this one is valid. No, this one needs to be thrown out. Keep in mind that if your hypothesis is proved false, that's a definitive answer. That's a definitive answer. If when Kepler proved that the concept of circular orbits was false, it was a false conceit, it was a cognitive bias thing. Everybody since Aristotle had been saying the universe functions on perfect circles because they're perfect. Yes, that is circular reasoning, friends, and Aristotle was proven wrong. Kepler himself threw out the elliptical solution to planetary orbits 3 different times over a period of 18 years because of this cognitive bias that it must be a circle. A good theory will allow you to sift functional hypotheses from false ones. Now, the trick is, of course, that you cannot prove a theory true. A theory covers everything we know about a vast area of knowledge, and to prove a theory true, you would have to prove it true in all cases, in all places, and ubiquitous throughout time. And we simply cannot, it is impossible to test something to that degree. For 350 years or so, people said Newton's theory of gravitation is perfect. It is unmodifiable. Anyone who challenged Newton's theory of gravity was laughed at. Well, this is silly. Newton is the most brilliant human being of ever. Of course his theory is right. What are you doing challenging it? And if you wonder why Einstein encountered so much resistance in the not only the intellectual but the physical and philosophical communities, it's because he said, oh yeah, the greatest mathematical mind in human history was wrong about his most famous theory. Einstein is famous, friends, simply because he was the first man in 350 years to successfully modify Newton's gravitational theory. And really, relativity only modifies Newtonian gravity when you have things which are moving very, very fast, or if they're extremely massive. Or, the third case, if they are extremely compact. So we're talking about things like things moving near the speed of light, or things that are as big as stars or as dense as neutron stars and black holes. So only under these extreme conditions do we set Newton aside and say, no, now Einstein takes over. If you want to fly to Mars, you're going to use Newton's theory. I believe it was in Apollo 8, which was going around the moon for the first time, and they asked the astronauts, who's driving? And one of the astronauts quipped, Isaac Newton is driving, because his theory of motion and gravitation was all they needed to get to the moon. They didn't need Einstein, because Einstein fits in the tiny little places where Newton doesn't work. Well, here we have this new theory from Professor Oppenheim that, we don't need to quantize gravitation. Instead, gravitation is going to normalize quantum theory on the very smallest level. Now, theories are great, but it's not a legit theory if you cannot test it and prove it false. Now, you may fail to prove it false. People have been trying to prove relativity false for almost 120 years, and they have failed every single time. But if relativity wasn't in principle falsifiable, if you could not say, oh, let's test it this way, and if it doesn't work, I'll get this result. If it does work, I'll get that result. And you've got to be able to test it. Theories which are untestable are not scientific theories. I have a theory that aliens regularly visit the Earth and abduct people for weird medical experiments. Well, is this falsifiable? No, it really isn't. Can you prove a negative? Can you prove something didn't happen? Prove I didn't go and kick a puppy into a mud puddle last Thursday.
See, Dr. Barth,
Sir?
I found that they just like to play poker.
Aha. I'm not a very good poker player. Matter of fact, I never play cards for money, never ever, because I'm just not one of my talents, my friend. I can tell you about probability. Can I actually sit there and manipulate the cards successfully? No, I cannot. And yes, I've tested that theory. But we're looking at this, and Professor Oppenheim says, yes, we can test this. It is in principle falsifiable, and therefore it's a good quality scientific theory. And essentially, Professor Oppenheim says if space-time is not quantized, if it's smooth and classical, if it's analog, well then, at some level, curvature of space-time must fluctuate randomly. It must have that quantum element in it. And if that's true, then mass is not a constant. I can take my pen here that we've been talking about, I can put it on a scale, and I can say, aha, this weighs 8.56732, and I can weigh the mass of this pen to a nicety. There are hyper-accurate scales which can get this to 10 or 12 decimal points. Professor Oppenheim says at some level of tininess, mass should not be constant. That in fact, if we put this in a sealed chamber where it was in a vacuum, where it wasn't subject to any outside influences and we could measure it very, very accurately, in fact, we would find that the weight of the pen, its mass, if you will, would oscillate and change and not be constant.
So question.
Yes.
If you ignited it, fire, the heat is energy. That energy was stored in the pen.
It would gain mass. If you put a pan of water on a stove and you're heating it from room temperature to boiling, and you cap that pan like a pressure cooker, and if you could weigh it accurately enough, you could measure the increase in mass, because Einstein says mass and energy are the same. If you're adding energy, you're adding mass. The problem is that the conversion factor is the speed of light squared. 3 million meters per second squared. So 3 million squared is a tremendously large number.
So
and when you make that a fraction, 1 over 3 million squared, you're talking very small indeed.
So wouldn't that confirm that mass is not steady?
No, because you're not weighing a mass, you're measuring a mass when you're adding energy. What we're talking about here is if we take a mass and we isolate it, so no energy in, no energy out. That means we have to maintain it at a very precise temperature, and we would probably pick a temperature near absolute zero, get it as cold as possible, and eliminate the possibility of energy, just basically shining a flashlight on a piece of paper. Some of that light is absorbed into the paper as heat, and the mass of the paper goes up. To date, no one has built a scale fine enough to measure such things. We understand that this is theoretically predicted. It is reasonable to assume that it does work that way, because every macroscopic measurement we've been able to make on whatever level has indeed said that our ideas about mass and energy and Einstein's theory. Every single test, the first relativity theory, special relativity, came out in 1905, general relativity in 1915. This is 2024, so we're talking 109 years for general relativity and 119 years for special relativity. Every single test, relativity has been proved correct and the challenger wrong. So we're looking at that, and Oppenheim suggests that this happens at a lot larger scale than you might think. We won't have to get down to the Planck scale. He predicts that it should be within our technology to build a scale that can measure this mass fluctuation. And I don't know, some of our viewers may know about the famous series of bets made by physicist Kip Thorne and Stephen Hawking about black holes. Did they exist? Could they be found? And their bet was usually for like $1 and a subscription to the magazine of your choice for a year. And Hawking won most of those. Well, in the spirit of this, Professor Oppenheim has a bet with Professor Carlo Rovelli, and he of quantum loop gravity, and Professor Jeff Pennington, who is the current master and champion of string theory. Both of these are alternate theories of gravitation at the ultra small scale, and they've given Professor Oppenheim 5,000 to 1 odds. I don't know, if I was Professor Oppenheim, I'd certainly be willing to throw a $100 bill in there at 5,000 to 1 odds. Maybe that's why I don't play poker very well. But indeed, all of these theories predict that space-time fluctuates. But Oppenheim's theory says this should happen at a much larger scale than is predicted by either quantum loop gravity or string theory. These two theories predict fluctuations happen at approximately the Planck scale, 10 to the negative 34th meters. Professor Oppenheim says, no, it's 10 or 15 or maybe even more orders of magnitude larger than that. And if Professor Oppenheim is correct, then he essentially says, wow, we should be able to build a device to test this sometime relatively soon. And this theory has consequences beyond gravitation. And when we talk about consequences beyond, my favorite one is J.J. Thomson, famous British physicist, who was given I think it's the very first Nobel Prize in physics for the discovery of the electron. Thomson was all about pure research, and he said that research should be sort of a gentleman's scholarly pursuit, and pshaw on all this technological development, and technology is unworthy of a pure scientist. And indeed, at his Nobel Prize banquet, where after he had got the prize, the toast he gave that evening was, "Here's to the electron, may it never be of use to anyone." And of course, all the firms, electronics, Sony, Apple, IBM, Dell Computer, all these companies that deal in electronics today, and it's all the internet is electronics, etc. So sorry, Professor Thomson, you were wrong there, my friend. But when we talk about the consequences, Professor Oppenheim's theory of postmodern quantum gravitation indeed has consequences. One of these is the Heisenberg uncertainty principle. Heisenberg basically says, gee, question?
No, it's not a question. When you said that, it just hit. I just giggled because I watched too much Star Trek.
Ah, indeed. So do I.
Which doesn't. I don't know if the Heisenberg uncertainty principles actually apply correctly in that TV show.
One of the few, yes. Yeah. One of the few. Heisenberg uncertainty principle, friends, basically says you cannot know everything all the time. Heisenberg's principle comes out of his work in quantum theory, and like Einstein, he got a lot of pushback because Heisenberg said, you can't know everything you want to know. No improvement in technology will help you. Nature fundamentally draws a veil over some things. The most famous version of Heisenberg's uncertainty principle is that you cannot know both position and momentum, or if you prefer the simpler version, position and speed at the same time. I used to teach this to students, and we would actually go into the gymnasium, and I had a box of 100 ping pong balls, and we had a camera, and we would go ahead. The room was dark. We had the flash set for a half a second, and I threw the ping pong balls up in the air and said, now, and they turned on the light, and the flash burned for half a second, and when you develop that image, you don't see ping pong balls, you see smears. Well, the smears, short smears are slow speed, long smears are high speed, and you can tell the direction and the velocity of the ping pong balls by looking at the smears. But where are the ping pong balls? They're somewhere within that smear. Their exact position over that half a second exposure is not determinable. Now we did a second experiment. Collect all the ping pong balls, kids. Put them back in the box. Let's set the camera flash for 1/1000th of a second, which was as fast as the camera we had would do. Throw up the ping pong balls in a darkened gym and say, now, poof, the flash goes off. Now you can see all the ping pong balls frozen in space. You can tell exactly where they are. But since you no longer have the smear information, you cannot separate the fast ones from the slow ones. You can't determine the direction. All this information about velocity, and which is speed and direction, has been lost. You've learned specifically about position, but you've lost the information on velocity. And so you can measure one or the other, but you cannot measure both at the same time. This is kind of like Gödel's incompleteness theorem, which is another mathematical idea that says you can't know everything all the time. Gödel and Heisenberg, excuse me, were both highly criticized. Pardon me. And so Professor Oppenheim says, gee, his theory may help resolve what's called the black hole information paradox. And quantum theory says information cannot be destroyed. It's like energy. Can't be created, can't be destroyed. You can't destroy information. Well, if I take my phone and I throw it into a black hole, certainly the phone is destroyed. But there's a whole lot of information in here. There's my contact list, there's pictures of my family and my dogs. There's all kinds of crazy stuff. Well, quantum theory says, and Stephen Hawking agreed, by the way, that this information would be re-radiated out of the black hole as it evaporated over billions and billions of years. But that's quantum theory. General relativity says, gee, once you throw your iPhone into a black hole, it's gone and the information is gone too. The loss of information is permanent. So is this is you is or is you ain't my baby? We ask Professor Oppenheim, is you is or is you ain't my baby, as the old jazz standard says. And the answer from Professor Oppenheim is, we'll see. What does he predict on his 5,000 to 1 bet? Professor Oppenheim predicts that we'll have an answer sometime in the next 20 years. So is to Professor Oppenheim, and I'm certainly hoping I'm still around in 20 years to find out whether you won your 5,000 to 1 bet. And I just think these things are fascinating. As usual, if you want more information, please download our episode guide, which is available on explorescientific.com. And there are links there in the show notes to all the various sites where I got the things from the news and the current theories. To wrap up today, do we have a couple of questions?
We had a few things.
Okay.
And looks like John Ray.
Yes.
He said, "Hello, Dr. Barth. Looking forward to this presentation. A copy of Star Mentor is loaned out when our Little Cornish Flat Library's telescope is borrowed." So
this is so exciting.
Yeah. And
John,
go ahead.
John Ray, at some point, my friend, you have to email me, Dr. B at explorescientific.com, and you've been so kind to donate your copy of Star Mentor, and you're with us every week. I'm going to make sure you get a signed copy, all for your own, just kind of as a recognition of your support of the How Do You Know program and the book. I really appreciate you, and you're there with good questions all the time. And I'm making a note. You email me, my friend, and a signed copy will go out to you, because you've been a great supporter of the program, and we appreciate that.
Connor Bradley, he says, besides the moon, what other moon is the moon in the solar system could we possibly set up a colony on?
Well, if you're talking about a moon in the outer solar system, Connor, you'd have to look at an underground settlement. If you're interested in the mechanics of space settlements, I highly recommend the book by Zach and Kelly Weinersmith called A City on Mars, and it goes into the technological, legal, and all sorts of other kinds of challenges for space settlement. But some of these distant moons with subsea oceans, I could certainly see them as a potential habitat. Phobos and Deimos, if you're interested in microgravity habitats, you have to be careful, because the smallest of Mars moons, you could probably almost pole vault into orbit there. But if you wanted a permanent habitat, say you wanted to set up and this has been proposed in science fiction, set up a circular railroad track running around, and if you run the train anchored like a roller coaster at the correct speed, and you're actually in the train habitat with your feet pointing out, creating a centrifugal gravitational field, yes, you could actually have a lovely habitat on one of the moons of Mars. And outside the habitat, you would have a very pristine microgravity environment. So there are many possibilities, but friends, if you're interested in that, highly recommend A City on Mars. I'm reading it now, and it's very fascinating and extremely well written. It's also fun and quite funny.
So we've also had a few people here from around the world. A gentleman from the Philippines is watching.
Outstanding.
Yeah, and we've got quite a few comments were deleted due to a technical issue when they're still out there in the Ethernet. They're not where I could find them at the exact moment.
Okay, that's fine.
The page crashed in the middle of the
You're
thing.
always welcome to reach out to me directly. Dr. B, B as in Barth, Dr. B at explorescientific.com. I'd be happy to answer you. Also, my author page, Astronomy for Educators at gmail.com. And when I get questions and ideas in, I do answer everyone. And as I think it was H.L. Mencken said, you certainly are welcome to ask impertinent questions as long as you don't mind impertinent answers. But yes, always happy to take questions. And there we are. It's another exciting episode of How Do You Know? I hope you'll tune in next week. We don't have a topic for you right now. We're working on that right now. But if you have something you would like to see discussed on How Do You Know, by all means, send me an email. Hey, Doc, could you talk about this? And I love suggestions from our listeners, as well as comments and questions. So that's pretty much all we have for this week. I hope you'll take a look and pick up your own copy of Star Mentor. And we'll see you again next week.